All right, so let's take a look at some applications that deal with some of those natural events that natural logarithms are used for. The population size y of a community of lemmings varies according to the relationship of y is equal to y sub 0 times e raised to the 0.15 t power. In this formula, t is the time in months, and y sub 0 is the initial population at time equals 0. This is a symbol that you'll see a lot, meant to be the original or the initial starting point where the time is just going to be beginning. Estimate the population after 6 months if there are originally 5,000 lemmings. So here's our 6 months, so that means this is our t. And originally, there's that word originally, 5,000 lemmings. So this is going to be our y sub 0. So we're looking now for the population at the end. So we're going to have y is equal to 5,000 times e raised to the 0.15, and then t is going to be 6. So I'm going to put times 6 right there. And then we'll go to our calculator and put that in. All right, so you need to calculate that. So we have 5,000, so 5,000. And then we can just put our e in, but we need to make sure not the e down on bottom now. You've got to use this e right here on the left. So push that, and it gives me the box up there for the exponent. And in it, I'm going to put the 0.15, and then I'm going to choose to use just the times right here on the right. So times and then 6. So notice that I don't need to multiply that out. I'm just going to put the multiplication up there and then just push enter to get my answer. And I am going to end up with 12,298 lemmings. All right, so here you have it. I have y equals 12,298 lemmings. All right, so let's go at it from a different direction. It says after how many months, so we'll be looking for here a t, will there be 30,000 lemmings? We want to figure out this will be y. So we already know that we initially had 5,000 lemmings, and we want to end up with 30,000. So when we fill our formula in, we're going to end up with 30,000 lemmings. That's going to be equal to 5,000 e raised to the 0.15 t power. And we need to calculate out what t is. So where is t? Well, t is in the exponent. And how do I get the t out of the exponent? I'm going to need to take the log of both sides. Now, the first thing I need to do, though, is I need to isolate my exponential expression. So you can see I've got this 5,000 right here, and I need to undo that. So I'm going to divide both sides by 5,000 in my calculator and come up with that answer for that. So I guess I can do that in my head. That's 6 is equal to e raised to the 0.15 t power. So now what I want to do to get the t out of the exponent is I'm going to take the ln of both sides. So ln of 6 is equal to ln of e raised to the 0.15 t. And again, e to the e power is going to give me the 0.15 t here. I'm going to put this in my calculator, get a number, and then I'm going to divide it by 0.15 to figure out what t is equal to. All right, so we want to calculate ln of 6. So we're going to do control e to the x and get a 6 in there. Then enter it. And then I need to divide that by, divide by 0.15. And enter it. And I get 11.9. So let's round it off to the number of months. And that's going to be 12 months for our answer. Now, hopefully I remember to do this, but I'm going to add continuous compound interest formula onto your into your notes. But this formula is A equals P E raised to the RT, where P is the principal that you start with, and A is the amount that you end with. R is the rate, and T is going to be the time. This is going to be compounded continuously. So remember before we'd say it was compounded every month, and we'd have a 12 in our equation, or every semi-annually, and there'd be a 2. This time continuously you have an E, which is going to take care of everything for you. So we'll look at that next time.